welcome to this video on material from section 5.3 for our Calc 1 Math 1431 course here at the University of Houston. And as I have here on my little title slide, this material is all about something called L'Hopital's rule. And first, what I'd like to do before we get into a bunch of examples is just tell you what L'Hopital's rule is all about. This is a rule that helps us compute tricky limits. So it's kind of weird if you think about this. Our journey through calculus began in a pre-COVID January, and we began then with talking about limits. We used the notion of limits to define derivatives and to talk about continuity, right? And in chapter 6, we're going to use limits to talk about integrals and areas. So that's chapter 6. But something kind of interesting is happening right now. What's going on here is, had we just stayed talking about limits from day one, we could have asked questions like, how do I take the limit, say, as x goes to 0 of, I don't know, something like x to the x. How on earth are we going to do this? Right? None of the ways we first talked about using limits help us compute this guy. What's so problematic about my orange example? Well, there's two competing rules, right? We have that 0 to any power is 0. That's one rule, so maybe this limit is 0. But we also have that any positive number to the 0th power is 1. So maybe the limit should be 1, or maybe it should be something in between. What the heck should this be? Right? It's unclear. This is a tricky limit. And so we started calculus talking all about limits. We avoided tricky limits like this one and said, well, let's just move on and talk about functions and continuity and derivatives. But now that you guys have worked so hard to understand derivatives, we can now use derivatives to circle back and answer this question. So we used limits to define derivatives, and now L'Hopital's rule is going to tell us how to use derivatives to secretly compute some limits. So this is a rule, as I wrote here in blue, this is a rule that helps us compute tricky limits. And how we do it, it involves taking derivatives. A little historical side note that nobody should care about, except that we're all home at bored at home and home all bored. So a historical note, L'Hopital, this guy, you can look this up, did not actually prove this rule. I don't just mean to say he wasn't the first person to not prove it. I mean he did not know how to come up with this thing we call L'Hopital's rule. Instead, he paid another mathematician. He paid someone else to prove it. And he bought the rights to use it. So I think it was Euler. He went up to Euler, famous mathematician, and said, hey, you're really smart. I think this is true. Why don't you be the one that proves it? Here's some money, and then I get to put my name on it. And that just goes to show you that in calculus, evidently paying for stuff is totally fine. That is a joke. Don't do that in calculus. That could really threaten your grade here. Anyways, okay, so let's go over, before I do that, before I get down to the notes and go over stuff, what are the tricky limits that L'Hopital's rule will help us figure out? So I mentioned it's going to use derivatives to compute tricky limits. And so here's what happens. In my example, we had 0 to the 0, right? That was when, I'll scroll up, when I tried to plug in 0 into that orange limit, x to the x. I'll get 0 to 0. I don't know what that means. That's tricky. There are some other ones where I also may not know what it means, like infinity divided by infinity. If I try to compute a limit by plugging something in and I get infinity over infinity, that's kind of unclear what that means. If I get 0 over 0, we've seen that one pop up a lot, but there are times when we don't know how to make sense of it. What does that mean? And there are times when we get infinity minus infinity. Yeah, so there's all sorts of forms, these tricky results we might get by trying to plug a value into a limit. And when we get one of these, that's a big sign that we should use what we're going to call L'Hopital's rule. I had a student several years ago who remembered this by calling it Floppy Towel's rule. Okay, so the first ones we're going to start with are infinity over infinity and 0 over 0. Then we'll get to some of the other tricky limits. Okay, so I just skipped past all the text. You can read that, but let me start with example 1a. I'm going to do this limit the way we've done it before, if we can. Oops, give me a second here. Sorry, gotta check something out before I set this problem up. Let's see. Nope. Okay. So this is kind of a weird one, but we're going to sort of manipulate. This one isn't too bad, but we can check if we plug in x equals 4, right? I'll get 0 on the top, and if you actually work it out on the bottom, you get 0. Okay, so we could have done this one the way we did before. That is, we might look at that degree 4 denominator and say, well, maybe I can factor that and cancel an x minus 4. You actually can do it that way. But let's practice doing this tricky limit the L'Hopital's way. So L'Hopital says, oh, you got 0 over 0. You should maybe use L'Hopital's rule, which I'll probably say that. What does L'Hopital's rule says? It says the original limit is equal to a new limit. It's equal to the limit of the derivative of the top function divided by the derivative of the bottom function. So in this case, what I'm really saying is, because we got 0 over 0, we say, well, maybe we should try L'Hopital's. And L'Hopital says you can compute this by taking a derivative of the numerator divided by a derivative of the denominator. And what the rule actually says is, if this new limit exists, that has to equal the old limit's value. And what have we learned? Well, unless our functions are really, really ugly, taking derivatives often simplifies functions. So after we take a derivative of the top and divide it by a derivative of the bottom, well, the top derivative is really easy. That's just 1. The bottom derivative is just 4x cubed. And now we can try to plug in x equals 4 and see if we get a number. And indeed, what we get here is 1 over 4 times 4 cubed. That's going to be the same thing, it turns out, as 1 over 256. So this is one way to use L'Hopital's rule in this one setting. I want to be really, really clear. When you get 0 over 0, because you were taking a limit of a fraction of a top function and a bottom function, if you ever get 0 over 0, then L'Hopital say, hey, try taking the limit of a fraction of the derivatives. And let me just say a word really quick about why this rule works without going into the proof that L'Hopital purchased. Why does this rule work? Here's what we're saying. I'll focus on this example. If you have a limit where x is going to some number, in part A it was going to 4, and you're comparing two functions, f of x divided by g of x, if this limit is trying to give you 0 over 0, what that's telling you is the numerator function and the denominator function are both getting really, really tiny. And so what really matters, if they're both heading to 0, What really matters is, well, who's heading there faster? Is f of x going at a faster speed or at a slower speed? If f of x is going really, really fast compared to g of x, then the limit might work out to be 0. If g of x is going to 0 much, much faster, the limit might work out to be infinity. If they're going at a sort of comparable rate, then the limit might work out to be some finite number. And so what matters is who wins the race. Well, how do you talk about speed? That's talking about the derivatives. So looking at this ratio of their derivatives is really asking this question, which function is going faster? And that's why L'Hopital's rule, in a sort of explanatory big picture sense, works. All right, so let's try another example. Oh, here's a great one. Example B. It has a weird looking function, and this is a great one because we want to practice differentiating this stuff. But first, this looks like a limit question. There's no derivatives involved right away, right? Maybe this is a question that popped up from way back chapter 1 or 2. Okay, but let's just try to plug in. So we're going to plug in x equals 0. And I get the 10 times the arctangent of 0. And I remember the arctangent of 0 is 0 divided by 0. That's 0 over 0. That's a sad face. I don't really know what's happening. But then it turns into a happy face because I get to use L'Hopital's. L'Hopital's rule says, okay, well, if that first limit was giving you 0 over 0, instead, do this new limit. The limit as x goes to 0 of the derivative of the top function divided by the derivative of the denominator function. Okay, so now I've got to remember what's the derivative of arctangent, and everybody remembers that. I'm just pretending like that's new. The derivative of arctangent is 1 over 1 plus x squared. The derivative of x is 1. And so I can simplify this fraction. This is really just the limit as x goes to 0 of this. And now when I plug in x equals 0, nothing bad happens. I get 10 divided by 1 plus 0 squared. I just get 10. So what's really going on, if you want to think about the original question? We're asking, okay, I've got these two functions, arctangent x, or 10 times arctangent x, and x. They're both heading to 0, and they're heading at about the same rate. The top function is going about sort of 10 times as fast, and so the result is 10. Okay, let's try this one. The limit as x goes to pi of 1 plus cosine of x divided by x minus pi. So, oops, sorry, I shouldn't say equal. Notice whenever I'm plugging in, I rarely use the equal sign because I kind of know when I plug in, I'm going to get a nonsense expression. I get 1 plus cosine of pi. That's 1 plus negative 1, so that's 0. And the point is I get divided by 0. And whenever I have something divided by 0, that's not a number. So it wouldn't quite be correct to say that this limit equals 0 over 0. I'm just trying to indicate when I plugged in this thing, I got a weird thing. I got a non-number 0 over 0. So now we floppy tails this, and we get that the limit should equal the limit as x goes to pi. The derivative of the top is negative sine of x, and the derivative of the bottom is 1. And as x goes to pi, we just get negative sine of pi, and that's just 0. So this new limit equals 0, which means the old limit equals 0. So what is this saying? This is saying the numerator function goes to 0 so much faster than the denominator that this 0 we saw appearing up here actually won the race and made the whole thing 0. Now, we weren't able to see that by just looking at this 0 over 0 expression. but appealing to the ratio of derivatives revealed that information to us. All right, let's try this example, example D. Let's try the limit as x goes to 0 of this function, 5 times e to the 3x minus 5 all over x squared. And if we plug in x equals 0, well, we get 5 times e to the 3, 0. Well, that's just 5 times 1 minus 5 all over 0, and I get 0 over 0. All right. So again, when I see 0 over 0, I am actually kind of happy now, because I can say, well, by L'Hopital's, I'll even label that equal sign, by L'Hopital's, I can trade this ugly 0 over 0 producing limit for a limit comparing its derivatives. And so what I'd really like you guys to do now is pause this video and see if you can finish working out this example. All right, I'm assuming you've at least given this a shot, so let's see how this works. The derivative of the top would be the derivative of e to the 3x is 3 times e to the 3x, so that becomes this number when I multiply by the 5, and the derivative of the bottom becomes 2x. And now when I plug in x equals 0, I get 15 times 1 over 0, which is 15 over 0. And after using L'Hopital's rule for a little bit, you might think, oh no, can I use L'Hopital's rule again here? Because it feels like it's a wrong expression, right? But this expression isn't 0 over 0. This is a non-zero number over 0. So L'Hopital's does not apply. L'Hopital's does not apply. Right? We need 0 over 0, or we'll see some of the other forms, but not non-zero over 0. So we have to remember, wait, what did we say we got as an answer when we were getting a limit that had non-zero number over 0? This was telling us the limit does not exist. And what's interesting, you might think that this is a failure of L'Hopital's rule for an example like this, but L'Hopital's rule is actually helping us here. It's telling us this original limit, which I'll try and circle in a blue color, this original limit doesn't exist. If this limit existed, then its L'Hopital limit, the limit of the two derivatives being divided, would exist. So this is good information. One last thing I'll point out, maybe I'll put it in green down here, just as another side note, is notice when we're using L'Hopital's rule, so when we use L'Hopital's for a fraction of functions, we don't take a derivative of the fraction. That is, we don't use the quotient rule, right? That's not what L'Hopital's rule is saying. It's not saying take a derivative of the whole fraction. We instead, we look at the fraction of derivatives. In my years teaching calculus, I haven't seen students make this mistake, but I just want to point it out since a lot of you are really good differentiators, and you might say, hey, whenever I see a fraction of functions and someone says derivative, I'm going to do quotient rule. L'Hopital's rule says you're comparing two functions with when you're taking the limit, and so now you want to compare their derivatives. You don't want to take a derivative of the whole compared fraction. Okay, so here's another form of L'Hopital's rule. I'll kind of skip all the words and focus on the examples, but here's the form, infinity over infinity. Again, if we have a fraction of functions, and they are headed to an expression we could call infinity over infinity, then we can apply L'Hopital's rule. All right, so let's try example 2a. So let's see. This one we could actually do without L'Hopital's rule, but I do want to maybe do it with L'Hopital's rule. Let's try, if you will, this is a little funny to say, let's plug in, and I'll put it in quotes, x equals infinity. Well, the numerator, if x is getting really, really big or really, really negative, the numerator x has an x squared, that becomes really, really positive. And then we have the square root of 1 plus a really big number. That's really big. Then we multiply it by 5, so this is really big. So as x goes to positive or negative infinity, the numerator goes to positive infinity. The denominator, as x goes to positive or negative infinity, goes to positive infinity too. And so first you might say, oh gosh, I've got infinities, that's ugly, but you want to start training your brain to be happy about this, because at this point you can use L'Hopital's rule. That's really, infinity over infinity tells you can use L'Hopital's rule. So I'm going to say this is equal to the limit as x goes to infinity of the derivative of the top function. I'm going to rewrite it a little bit. Okay, so now you got the derivative of the top function divided by the derivative of the bottom function. That's what L'Hopital's rule says for these. So now I've got to do a little bit of calculus to compute these. All right, so I'm going to take a derivative of this numerator function. There's going to be some chain rule involved. I bring the 1/2 down, multiply it times 5. I subtract 1 from the 1/2. Then I multiply by the derivative of x squared. Then I divide by the derivative of that denominator function. That one's not too bad, that's just a 12x. And one thing you can see that's going to happen that's helpful here is that these two x's are going to cancel. And then I just have to rearrange those numbers to see what this limit maybe is going to look like. So this would be the limit as x goes to infinity. Alright, so let's see. I have a 5 times 2, but some of those 2's can cancel. So that 2 can cancel with that 2. So I have a limit as x goes to infinity of 5, and then I have a 12, and I can put that 1 plus x squared in the denominator with a positive 1/2. And now we can say, okay, as x goes to infinity, x squared goes to positive infinity, and so 1 plus x squared goes to positive infinity. The square root of that goes to positive infinity. 12 times that goes, so the denominator is going to positive infinity, and so we're going to get 0. And really what happened here is, if you wanted me to write this, I got something that looked like 5 over infinity, but a number divided by infinity, that's a finite number divided by a very big quantity, that goes to 0. So again, L'Hopital's rule is useful here. Why is L'Hopital's rule working for this infinity over infinity case? It's the same reasoning. If you have two functions divided by each other, and the top one's going to infinity, but the bottom one's going to infinity, just like when they were both heading to 0, what matters is who's winning the race. Is who wins the race. And with this, when I talk about race, that talks about speed. So yeah, it's weird that both functions are getting really, really big, or maybe one's getting really positive and the other's getting really negative, but they're getting really, really not finite. But what really matters is the top one becoming infinite faster than the bottom one? Or is the bottom one becoming infinite faster than the top one, right? So L'Hopital says, right, all you need to do is compare their derivatives. So if I go back and look at example 2a, what this limit tells me is that this denominator function was going to infinity so fast, it more than compensated for the fact that the numerator was also becoming infinite. The denominator was going to infinity so quickly that the whole thing still went to 0. All right, let's try another example here. Sorry, I keep hitting my microphone. The limit as x goes to pi over 2, and this is an interesting one, from from the left, so we'll be sure to pay attention to that, of the function secant x divided by 1 plus tangent x. Okay, well first, let's just try to plug in. If we plug in pi over 2, the secant of pi over 2, that's 1 over the cosine of pi over 2, and cosine of pi over 2 is 0. So secant of pi over 2 is 1 over 0. So that's going to be like a plus or minus infinity on top. And the tangent is going to go to, also, it's going to be a plus or minus infinity. So we just want to figure out, is it plus or minus infinity on the top, and minus or plus infinity on the bottom? What are the signs of these ugly infinities before we L'Hopital's it? Well, I'll draw a graph of, I guess we'll do tangent x maybe in light blue. So there's a tangent x, a piece of it. So you can see from this graph that tangent x, as you go to pi over 2 from the left, the tangent x values go to positive infinity. So this is going to be positive infinity. And if I make a quick graph of roughly what secant x looks like, it's going to look something like this, at least the part that I care about here. It's going to look something like that. And so similarly, secant x, as you go to pi over 2 from the left, its values go to plus infinity. So both of these were actually plus infinities. So this became infinity over infinity. Okay. And so in either event, even had these been a mixture of types of infinities, L'Hopital's rule says, okay, you got some type of infinity divided by another type of infinity. So this one-sided limit equals this new one-sided limit. The derivative of secant divided by the derivative of 1 plus tangent. And the derivative, now we got to remember all of these. The derivative of secant, if I'm not mistaken, is secant x times tangent x. And the derivative of tangent is secant squared of x. I think I got those right. Those sound right. All right, so before we plug pi over 2 back in, we can try to clean this up a little, make this look a little nicer to evaluate. I can certainly cancel a secant x from the bottom and the top, and so I get tangent x divided by secant x. And it's true, if you plug this in right now, you're going to get infinity over infinity. That's going to happen. In which case you might say, well, I'll use L'Hopital's rule again. And you absolutely could try that, right? There's no restriction on the number of times you can try to use L'Hopital's rule. But one thing I would recommend, when you have trig functions just like this, maybe let's write them out in terms of sines and cosines to see if anything else cancels. So that tangent x is a sine x over cosine x, and that secant x is a 1 over cosine x. So some of you are already going to say, oh, those cosines cancel. Some of you will say, well, wait, write that out a little bit so I can see that. And so let me write that out a little bit differently. I've got a sine x times a cosine x, all divided by a cosine x. Right? All that happened here was some algebra. This 1 over cosine x comes up top. This over cosine x I can write down there. In any event, I get to cancel these cosine x's. Oh, and I forgot to plug in this thing going from the left. And so finally, it turns out, after using L'Hopital's and simplifying my trig functions, I'm just asking, hey, what's the limit as x goes to pi over 2 from the left of sine of x? And this just happens to equal 1. So what does this say? The original limit, this original limit way at the top here next to this letter B that I'm now circling in orange. That limit we learned using L'Hopital's had to equal 1. Okay. in terms of a race, what is that saying? That's saying the functions really are tied. As x goes to pi over 2, the functions head off towards infinity at a completely balanced rate. All right, here's a great one. X goes to infinity of the natural log of x all squared. So I'm going to rewrite this a little. It's a weird way to write it. This is the limit as x goes to infinity. I think what they mean here is the natural log of x, square that, all divided by x. And if we plug in x equals infinity, put that in quotes, because it kind of pains me to write it, I get the expression, well, the natural log of infinity, I'll let you think about that, why that's going to be infinity, and then x is clearly going to infinity. So I get to use L'Hopital's rule. So by L'Hopital's rule, this limit equals this new limit. The derivative of the top function, so that's the natural log of x all squared, and now I gotta prime it, divided by the derivative of the bottom function. The bottom function is pretty easy to take a derivative of. The derivative of x is 1. Now the top function isn't that bad either. I just have to do a chain rule. The outside function is a power function, raising to the second power. So I bring the 2 down, and then I multiply by the derivative of that inside function. And so what do I get? I have 2 times the natural log of x times 1 over x. Alright, so now I have the limit as x goes to infinity of 2 natural log of x divided by x. And here's a great thing. Now you say, okay, I did L'Hopital's rule. Now let me plug in, and I'll switch colors because I'm getting tired of looking at all this red. Now let me try to plug in again. X equals infinity. And what do I get? I get infinity over infinity again. Okay, so I can either give up or I can say, well, I'm going to use L'Hopital's a second time. And so now, after using L'Hopital's a second time, I'll have the derivative of 2 natural log of x divided by the derivative of x, taking a limit of those two as x goes to infinity, and we can simplify this quite a bit. The derivative of 2 natural log is 2 over x. The derivative of x is 1. And finally, we arrive at a limit that is super easy to take. After using L'Hopital's rule twice, we learn that the limit is 0. So the limit of this expression is 0, which by L'Hopital's rule means this limit was 0, which by L'Hopital's rule means the original limit was 0. Okay. Before we do some of these forms, let's pause and do a popper question. So let me throw in a page here. So this will be popper question 1. Okay. If the limit as x goes to 7 of a fraction of functions has the indeterminate form infinity over infinity, and the limit as x goes to 7 of f of x, of f prime of x is 8, and the limit as x goes to 7 of g prime of x is 2, then what does L'Hopital's rule tell us the original limit? Oh, I said an infinity. I meant a 7. The original limit had to equal. Is it A, 4? Is it B, 1/4? Is it C, 0? Is it D, a limit that does not exist? Or is it E, none of these? So take a moment to think about this. I'm saying suppose you have f of x divided by g of x, and that fraction tries to go to infinity over infinity. And then I'm telling you this new information. The limit of the derivative of f of x is 8, and the limit of the derivative of g of x is 2. I claim you can use L'Hopital's rule in this situation, and it should tell you the right answer here. Let me do another Popper question since we have it up with some space. Popper question 3. This one I'll make a review one since we've gone through just a crazy amount of material already. What is the derivative of the arctangent of e to the x? Kind of an ugly one. Let's see, is the answer choice, I don't know, I'll give you some. Is the answer choice A? Is it 1 over 1 plus e to the 2x? Is it B? E to the x over 1 plus e to the x? Is it C, e to the x over 1 plus e to the 2x? Is it D, the sine of the natural log of x? Or is it E, none of the above? And for those of you who like the facts that I'd like to use different colors when presenting my Popper option answers, worry not. The lovely display of colors and all the lovely information you might be getting from them, it may be absent from this question, but I might find other ways to help you towards some super helpful information. Yeah, so there are other ways to communicate how I want you guys to proceed. But okay, oh my gosh, look at all those marks. Let's get rid of all those ugly marks. All right, let's keep going with L'Hopital's rule. Oh. All right, so here's another indeterminate form. The 0 times infinity. What if you get a tricky limit that looks like that? By the way, our textbook and our notes like to use this word. I've slipped it in a little bit. Indeterminate form. That just means tricky. When you plug a number into a limit and you get one of these tricky expressions, if you want to sound like a nerd, you say it's an indeterminate form. You don't know what it is. So, let me show you through an example how we can figure this one out. All right, so again, L'Hopital's rule can handle this case, but we need to do a little bit more work to it before it completely gives it to us. All right, so example 3 is a good one to test this on. Let's take the limit as x goes to infinity of this product. Not a dividing two functions, but now we're multiplying two. And when I plug in x equals infinity in quotes, I get infinity times, okay, the sine of 1 over infinity. I actually can work that out a little bit. That's infinity times the sine of 0. Oh, I know what that is. That's infinity times 0. And so whenever you get a tricky indeterminate form like this, you want to be happy. You want to think L'Hopital's rule. This is another trigger for L'Hopital's rule. Okay, but how on earth are we going to do this one? So far, L'Hopital's rule has only been good for 0 over 0 or infinity over infinity. So how are we going to do 0 times infinity? And it turns out we're going to rewrite this as one of these cases. So before we apply L'Hopital's rule, we need to rewrite this. One way we can do this for this example is, now I'll switch to my ugly red marker, is before I even try any L'Hopital business, I could rewrite this limit that x squared out front, I could write as 1 over x squared. This is one of the dumbest tricks to do, because we have to admit, this used to be a nice looking x squared, and then I did 1 over it and put it in a denominator and made it look like this lower limit. That makes these expressions look worse. Most of the time, rewriting a function like this where you cause an unnecessary denominator is like a taboo move. You don't want to do that most of the time. But for this case, it can actually be helpful, because look what happens now when I plug in x equals infinity. Well, now I have sine of 1 over infinity in the top. That we already said was 0. But now in the bottom, I get 1 over infinity, which is the same thing as 0. And so now I'm very, very happy, because, like, I'm angry happy, because this is a L'Hopital form. This is a tricky form where I'm allowed to do L'Hopital's rule. And so now I can apply L'Hopital's rule, and I will get that this is equal to the limit, as x goes to infinity, of the derivative of sine of 1 over x. Okay, we're going to have to figure that out a little bit. Divided by the derivative of 1 over x squared. So let's work out some of those derivatives. So the derivative of sine of 1 over x squared, that's going to be a cosine of 1 over x times, and the derivative of 1 over x squared, you can use quotient rule or power rule, is negative 1 over x squared. And now, from the bottom, I've got to do the derivative of 1 over x squared. That's going to be negative 2 over x cubed. And this limit, if you try to plug in, leaving all the functions written the way we have them now, we get 0 over 0. So before I try and plug in, let me see if I can rearrange, right? Because I got a bunch of fractions running around. I'm going to leave that cosine of 1 over x floating around. But that I have an x cubed, like, in the denominator of a fraction that's in the denominator, so that x cubed can come upstairs. And then that negative 1 over x squared, that x squared from upstairs comes downstairs. That negative 1 and that negative 2, the negatives cancel, and I get this. And what's nice here is I can cancel some x's, right? I can say, oh, I've got 2 x's down below and 3 on top. So this now becomes the limit, as x goes to infinity, of cosine of 1 over x, say divided by 2, just times x. And here's where, if I plug in, again, I'm going to put it in quotes, x quote-unquote equals infinity. What I get here is, well, the cosine of 1 over infinity, that looks weird to say, times infinity, but the cosine of 1 over infinity, that's just the cosine of 0. And the cosine of 0 is a number, that's just like 1/2. And what is 1/2 times infinity? That's just going to infinity. Right, so this is here, this will now start to feel like a trick. Once you get here, you might think, oh, again, do I need L'Hopital's rule again? No, L'Hopital's rule doesn't handle this. There's not a race here, right? You have one part going to the number 1/2, the other part's just getting big. So the whole thing's just getting big. There's no race. And so what we learn here is that after applying L'Hopital's rule and simplifying, we learned that the limit does not exist. Right? And if you go back and think about this rule in general, 0 times infinity, of course that's a race. You have one function going to 0, the other function's getting really, really positive or really negative. So it really matters which function is getting there first. And in this one, we would say the function that was heading to infinity was winning. All right. Here's another tricky form. If you plug in and you get infinity over infinity, then you can, infinity over infinity. If you plug in and you get infinity minus infinity, then you can rewrite this formula so that you can turn it into, again, a previous one, 0 over 0 or infinity over infinity. Okay, so to evaluate this limit, if it exists, what we would first want to do is maybe write this as using a common denominator. So what's missing from the first fraction's denominator? It's an x minus 1. So maybe I'll put that in. I'll put in x minus 1 times log x. And what's missing from the second fraction's denominator? Natural log x. Right, this is my cheap way of always making a common denominator. And I'm not saying this is the lowest common denominator, but it's a way that always works. So this is what I always try. So now I can combine the two stuff on top. I'll have x minus 1 minus the natural log of x times this stuff. And here's what we can see happens. If I had tried to plug in 1 into the original, right, into here and into here, then I would get, I'm just going to write across the text, I would get that this limit goes to 1 over 0 minus 1 over 0, which you could call, oh, that's going to infinity minus infinity. But now, if I plug in at this step, after rewriting, this now goes to, I got to be careful plugging in, x minus, let's see, if I plug in 1 for x on the top, I'll get 1 minus natural log of 1, all divided by 1 minus 1 times natural log of 1. Well, 1 minus 1 is 0, and the natural log of 1 is 0. So I get 0, and on the denominator I get 0, and now you're super duper happy, right? You've got these like Pac-Man old pie eyes, and this super crazy corona-infected smile. You're happy at seeing 0 over 0, because you get to use L'Hopital's rule. So we're going to apply L'Hopital's rule to this red mess, and here's what we'll get. The limit as x goes to 1 from the right, the derivative of the top. The derivative of x is 1. The derivative of that negative 1 is 0. And the derivative of natural log of x is 1 over x. Now I've got to differentiate all that stuff in the denominator. You definitely want to hit pause here and try this out for yourself, and then play the video to see if our answers look the same, just for getting that derivative of the denominator. Okay, so hopefully what you use for the denominator derivative is product rule. The derivative of x minus 1 is 1, so that's going to be a 1 times natural log of x, plus x minus 1 times the derivative of natural log of x. And let's see what this equals, if it equals anything nice. If you plug in 1, right, you will still get 0 over 0. Maybe we'll have to use L'Hopital's rule again. Oh, I didn't even mention we were using L'Hopital's rule, sorry. Maybe we'll have to use L'Hopital's rule again, but maybe we can rewrite some of the top thing. Maybe not. Let's see. Maybe I can at least rewrite this a little bit. This will be the limit as x goes to 1 from the right, 1 minus 1 over x, all divided by the natural log of x plus 1 minus 1 over x. Okay, so let me hit pause on this because I've run out of room, and I gotta insert a new sheet of paper. And let me rearrange this paper, this new page. So I'll have to pick this up down below. Okay. Let me make sure I didn't make any mistakes before we keep on with that. That would be x minus 1 log x. Sure. Oh, sorry. Okay, so this is example 4, so let me continue with example 4. So example 4 continued. So we were right here. The limit as x goes to 1, I believe from the right. Is that right? Or from the, yeah, of 1 minus 1 over x, all divided by the natural log of x plus 1. All right, we'll see if I get stuck on this example. But right now, when I plug this in, when I plug in x equals 1, I appear to get 0 over 0. So maybe I can use L'Hopital's rule again. Maybe I'll try it that way. And when I do that, the derivative of the top is 1 over x squared, and the derivative of the denominator, well, the derivative of natural log is 1 over x, and the derivative of minus 1 over x is 1 over x squared. And this looks a lot better because when I plug in x equals 1, I get 1 over 1 plus 1. I get 1/2. So I use L'Hopital's rule twice, and just keep in mind the indeterminate form that we were addressing here was infinity minus infinity. Okay, so I'm going to have to scroll around a little bit because what I'd like to do is just summarize the 3 cases we've talked about, 4 cases for L'Hopital's rule. So when you have 0 over 0, or any type of infinity, plus or minus, divided by any other type of infinity, you're going to use L'Hopital's rule to get this limit, f prime over g prime. If you have 0 times infinity, or infinity minus infinity, you rewrite it. Right? What we did with our infinity minus infinity, we put it over a fraction, and I think we ended up getting 0 over 0. So this can be rewritten as one of these 2 types. Similarly, for our previous example, we did 0 times infinity, and we were able to rewrite this. There are 3 other cases that I want to talk about, so this makes this video a little longer. And one of them I mentioned at the very beginning of these notes, and that's 0 to the 0. But there's another one, just want to get the right order, 1 to the infinity. And then the last one I believe is infinity to the 0, right? So these 3 cases you can also handle with L'Hopital's rule. These look very different than the 4 cases written right above, right? Here's what we're going to be able to do, though. Using logarithms, so natural logs, these look like the ones above. So, these extra weird indeterminate forms, these tricky cases of 0 to the 0, 1 to the infinity, or infinity to the 0, if you first introduce a natural log, you'll be able to pull these tricky exponents down in front, and that'll make it look like one of these cases up above. So that's how we're going to proceed with these cases. I just want to make a quick comment that for these 3 other cases, right, these are also races, right? Because if you have a function and it's heading to 0 to the 0, just like we mentioned, what wins? Should this be 0? Because 0 to any power is 0? Should this be 1? Because any number to the 0 power is 1? Should this be something else? Similarly, think about this guy. If you have an expression that's going to 1 to the infinity, well, it kind of depends on what's doing more of the work. Are you going to the number 1 really, really fast so that this is just 1? Or are you going to the number 1 through numbers like 2, 3 halves, right? Like that. But you're going to powers that are bigger and bigger. Maybe this could be infinity, right? For each of these cases, there's 2 competing rules or ways to think about it. And so all of these involve a race. What we're sort of asking is the limit is going to depend on, is the base going to its value faster, or is the exponent going to its value faster? And that's a big clue that we can somehow use L'Hopital's rule. Okay, so let's start thinking about these next 3 cases. Let me walk through example 5. I'll try to write small so that we have enough room here. If I plug in x equals 1, I will get 1 to the 3 over 0. That looks like 1 to the infinity. And what your brain should say is, that makes me happy. I can use natural log LOHOP. So here's the way you're going to work it. I'm going to write actually a little more than you guys will be required to write. So you're trying to do the limit as x approaches 1 of this weird x to the 3 over x minus 1. And what you're instead going to do is you're going to say, I don't want to do that limit. Let me take the natural log of all of that first. Here's the good thing about the natural log function. It's continuous. So the natural log of a limit has to equal the limit of the natural log. So I like to tell students what you're really doing is you're taking a natural log of the whole thing and then bringing the log inside the limit. Why is this a good thing to do? Now I switch colors. This is a good thing to do because of our logarithm rules. I did not switch colors. Our logarithm rules tell us that the natural logarithm of something to a power, you can bring the power down. And now I just have a natural log of the base. And now look at this new limit that I've written in green. Right? I haven't L'Hopital'd anything. I just took a natural log, brought the power down, and now when I try to plug in x equals 1, look what I get. I get 3 over 0. I get infinity times the natural log of 1, which is 0. You could also rewrite this limit, right, as saying, wait a minute, that's the limit as x goes to infinity of 3 ln x, all divided by x minus 1. And this clearly goes to 0 over 0. So when I wrote it above like this, I got infinity times 0, but I could quickly rewrite it to get 0 times 0. Both of these indeterminate forms tell me you should use L'Hopital's. So I'm going to use L'Hopital's rule, and I get to trade this limit for the limit where I have the derivatives being divided. So the derivative of the top is 3 over x, and the derivative of the denominator is 1. This actually turned into a really simple limit to compute. The limit, as x goes to 1, of 3 over x. And this is just 3. Now here's the thing, there's a big warning, so I'm going to put this in red. This is not your final answer. And of course, I promise you, these old quizzes and homework questions will have, if this were your question, it would have 3 as a possible answer. They want to trick you. They want you to pick 3. 3 is clearly related to the final answer. But this is what we just did. If you start where we ended in 3 and trace all the way through the green stuff and back through the black stuff all the way up here, what we answered, what we said is that the natural log of the limit we wanted, right? We took a natural log of everything first. The natural log of the limit we wanted was 3. But the problem didn't ask us, hey, what's the natural log of this limit? It wanted us to do, what's the limit? So we need to get rid of this natural log. if only the department had been smart and helpful in planning this material so that we had talked about how to get rid of natural logs. What's the, like beforehand, what's the inverse of natural log? That's right, e. So to get rid of this natural log, you do e to the both sides. E to the natural log, that kills that, and then I get an e to the third power. So the limit I was looking for, the limit as x goes to 1 of x to the 3 over x minus 1, that's just e cubed. That's my final answer. These questions are great, I love them, but it's really easy to forget to stop here in green and forget you've got to undo that natural log you first put in there. Right, and let me put in a little cross mark here. Right, this e and this natural log completely cancel each other because they're inverses. Okay, not too much more from these dense notes, so let's keep going. Actually, before we keep going, let's maybe do, I think this will be our third popper question. You might want to look away from your screens while I look for our previous popper question. So I got to scroll around. Yeah, we had, oh no, this will be our fourth popper question. Okay. Good thing I looked. Okay, so our fourth popper question, popper question 4. Just rewrite, that is simplify, something like the natural log of sine of x all to the x power. What does that equal? Does that equal a, x times the natural log of sine x? Or does that equal maybe b? Does that equal sine of x times the natural log of x? Does that equal c, the natural log of cosine of x? Does that equal d, 0, or is there no right answer here? That's our fourth popper question for this one. Okay, let me scroll now. We have 2 more cases to consider for this L'Hopital's rule. All right, so the 0 to the 0 case. That's one that's going to allow us to do L'Hopital's rule. Let's try this limit. When I plug in x equals 0, sine of 0 is 0, and that exponent is 0. So this suggests take a natural log, then do L'Hopital's. So what I'm going to say is that the natural log of the limit as x goes to 0, I guess from the right, of sine of x all to the x, I'm going to then say, okay, I can switch the limit in the natural log, because log is continuous. I have too many parentheses. And now I can use my logarithm power rule to bring that silly power down. And now I have this. And now when I plug in x equals 0, I will get 0 times the log of 0. That's something you really do want to remember. What's the natural log of 0? That's negative infinity. And so if I rewrite this, right, I have 0 times an infinity. That tells me I'm going to be able to use L'Hopital's, but I just need to rewrite it a little bit. So I'll get the limit as x goes to 0 from the right. Maybe I'll write this as the natural log of sine of x. And I'm going to force that x that's becoming a 0, I'm going to make that be a 1 over x. Right? So that this now goes to the natural log of 0 divided by 1 over 0, which is infinity. So now I can use L'Hopital's. Okay, so this now becomes, by L'Hopital's rule, the limit as x goes to 0 from the right, the derivative of the natural log of the sine of x all divided by the derivative of 1 over x. And when I do this, I've got to do some chain rule stuff. So the derivative of natural log is 1 over, and then I have to multiply by the derivative of sine, which is cosine. In the denominator, I get the derivative of 1 over x is negative 1 over x squared. And so, of course, I should probably rewrite this a little bit. I get the limit as x goes to 0 of, maybe I could write this as negative x squared cosine x all over sine of x. Okay, so this limit is taking a little more work. That's okay. A bit more algebra. If I plug in x equals 0 to this, I will get 0, because 0 squared is 0, times cosine of 0, that's 1. So I get 0 on the top, divided by sine of 0, which is 0. Hooray! All right, so we might want to rewrite this, but we might want to do L'Hopital's rule again. And let's see if I want to do L'Hopital's rule here. The derivative of the top would be negative 2x cosine x minus plus x squared sine of x. And that's all over the derivative of sine of x, which is cosine of x. And so this, now, when I plug in x equals 0, on the top I get 0 times cosine x, so I get 0 plus 0 times 0, so I get 0 on the top divided by cosine of 0. Oh my god, I finally get 0 after using L'Hopital's rule twice. But I want to point out that is not the final answer. What we have, and this is why I always introduce this, we found the natural log of the limit equaled 0. So we've got to undo that natural log. So we found that the natural log of the limit as x went to 0 from the right, what was this, sine of x to the x, we found that the natural log of this limit was 0. So now I've got to do e to the both sides. These will cancel, and I will get that the limit I'm after is just e to the 0, which is 1. That's my final answer. All right. I think this is among our, yeah, then we just have a summary there. Okay, so this is our last example. I need to end this video soon because I'm sure it's going to take forever to upload. But let's try this one, and then we'll do a final popper question. So example 7 says, evaluate this limit if it exists. Okay, so let's see. If we plug in, let's try a nicer color. If we plug in, again in quotes, x equals infinity, then this becomes infinity to the fourth plus 1, that's infinity, and that's the natural log of infinity. You do want to keep this in mind, is just it's just infinity. So this looks like infinity to the 1 over infinity. So that looks like infinity to the 0. And that's one of our cases that we should know about, that we should know requires L'Hopital's. I like to say it doesn't just require L'Hopital's, it requires a natural log and then L'Hopital's. So let's do the natural log of this terrible limit. So x to the fourth plus 1, all to this bizarre power. And then we bring the natural log inside. So now I have the natural log of x to the fourth plus 1. And I had that weird power up front, but it came down, right? So I had this power up here, but then it comes down and I get a 1 over natural log of x. So what I'm really looking at here, let me switch colors to keep, I don't know why, it's seems to me that these colors are getting more annoying the longer I stay with them. Okay, so as x goes to infinity, I look like I'm looking at the natural log of x to the fourth plus 1 divided by the natural log of x. Alright, so now we might want to plug in x equals infinity to see what this goes to. That goes to the natural log of infinity divided by the natural log of infinity. That goes to infinity over infinity. That is a great candidate for L'Hopital's rule. So by L'Hopital's rule, we get that this limit equals the limit as x goes to infinity. I'll write this out a little bit. The derivative of the numerator divided by the derivative of the denominator. Alright, the derivative of the numerator is 1 over x to the fourth plus 1. That's going to all be in the numerator. Times the derivative of x to the fourth plus 1. That's our chain rule appearing. And then it's all divided by 1 over x. And so let's see if we can sort this out. We'll get the limit as x goes to infinity of 4x cubed divided by x to the fourth plus 1. But then that 1 over x, I guess, could come up here to an x to the positive 1. And so if I rewrite that, I will have the limit as x goes to infinity of 4x to the fourth over x to the fourth plus 1. And now we're panting, or at least I am. And what I have here is an old limit where x is going to infinity we talked about a while ago. So x is going to infinity, but this is just what we called a rational function. We just looked at the highest power with its coefficient and the highest power. They completely balance, so we just get 4. Alright, so popper 5, my last popper here. Popper question 5. This is example 7. What is the answer to example 7? Is it, as I just stopped up above, A, 5, A, 4? Is it B, actually was it somehow infinity? Is it C, e to the fourth? Is it D, 0? Or is it E, none of the above? Alright guys, that's going to do it for this video. It's clocking in at about an hour and 13 minutes. Dear me, that's like a full class period. Alright, I hope you guys continue to do well. I know many of you are still trying to figure out our online stuff, so I appreciate your patience and working hard. Please hang in there. Please keep trying to figure things out. Please keep trying to stay up with your work. It's not that I think you have no other things that are more important. You likely do. And I want to be as sensitive to that as I am allowed to be, that is, as I can be. Right now, the university and the math department are having its instructors offer course material the way we are, and continue having you guys go through this material as though you're showing up in class and as though you're not worried about your family, your safety, your health, or your jobs. And I don't know that there's a better way for them to do it, but I do understand this calculus stuff. I love it, but it may not be and probably shouldn't be the most important thing on your mind right now. When you have time for it, please give it as much attention as you're able to. And I hope I can continue to make it worth your while, at the very least as minimally stressful as it can be. Alright, I'll talk to you guys later. Bye.